So in the previous video, we discussed about the various aspects of matter, gave you an introduction on the physical properties of dental material. Then we discussed a little bit about the stress, strain and other properties related to these two factors. So today's discussion is focused more on the strength and hardness of a dental material, and then we'll end with a note on the color related properties of dental materials which is needed for aesthetics. Now, flexibility or maximum flexibility is the strain that is produced in a material when that particular material is stressed to its proportional limit. So, the importance of this property is going to come in a restorative material. So, a restorative material, especially in the posterior teeth, has to withstand high stress, especially the masticatory stress, while undergoing minimum permanent or plastic deformation. Now, in case of an impression material, especially the elastomeric impression material, when the impression is withdrawn from the undercuts of the mouth, it should not undergo any deformation. This can be calculated by the formula proportional limit divided by modulus of elasticity, or EM equals P by E. Resilience again is an amount of energy. So, when a material is stressed before or within its proportional limit, it will develop a energy which is absorbed by it. That is called as the resilience. So it is also called as springiness because it kind of like a recoil tendency is still retained by the material. So if you want to talk about this resilience, it is measured by means of the modulus of resilience. So this is the amount of energy that is absorbed and stored by it per unit volume of that material when it's stressed to its proportional limit. So if you want to represent this resilience or you want to measure resilience, when the stress strain graph is plotted, the area under the straight line portion is the resilience. So now the modulus of resilience can be measured as R equals P square by 2E. Impact is actually the reaction of a stationary object in response to collision with a moving object. So it's like a stationary car or a car which is standing in a traffic signal gets like hit by a car which is coming very fast. So that reaction of the stationary object, how far that stationary car is going to move, is the impact that is produced by the moving object. So now this impact is dependent or based upon the resilience of the object. Now based on this, there can be deformation or there cannot be deformation. Now an ability of the body to resist this impact without any permanent deformation. So it can be represented by KVR. So here K is the constant of proportionality, V as we know is the volume, and R as we saw before is the modulus of resilience. Now we know that R equals P square by 2E. So according to this, impact resistance or KVR can also be calculated by KVP square by 2E. Now, we know the formula. So from this, what can be inferred? So it can be inferred that the modulus of elasticity is inversely proportional to the impact resistance. That is, when impact resistance falls, the modulus of elasticity is going to raise. So from this, it means that a stiffer material is going to have less impact resistance, whereas a resilient material is going to have a better impact resistance. Again, the volume and impact resistance are directly proportional to each other. So, what is the importance of this impact strength? Why we should know? So, the impact strength is the energy which is required to fracture a material. So, when an impact is experienced by a material, a particular energy is required for its fracture. That is what is called as the impact strength. So how do you measure this? So it can be measured by two methods. First is the Sharpie impact test. So here you can see that there is a pendulum. This is going to move and hit the specimen, causing it to fracture. So that energy is going to be measured by means of the gauge here, and you can calculate the impact strength by this. Second method is ISOD impact strength. So here there is going to be a notched material to which the pivoting arm is going to swing and hit, and from that the energy is calculated. So again, what is the significance of the so-called impact strength or impact resistance? So when any denture or a process is made for a patient, it should have sufficient impact strength and it should be resilient enough to facilitate like a survival after a fall. That is, if the patient unintentionally drops it or there is an accidental drop of this prosthesis, it should not break. If it breaks, then the full purpose is lost. So it should have sufficient impact strength to withstand that fall. Next is permanent deformation. So now, when a material is stressed beyond its proportional limit, it is prone to develop a permanent deformation. So it can be defined as a permanent change in the dimension of a material on application of a force or stress. So what happens? So with a particular amount of strain, I am going to expose that particular material to stress. This is going to result in an increase in strain. So at this point, the stress and strain are no longer proportional to each other. So as a result, there is permanent deformation. So again, what is the significance of this? So an elastic impression. So when an elastic impression or any impression is made, there is, to an extent, there is a deformation of that impression. So how better it is going to recover with how much little deformation? That is very important to like help in the indication of various impression materials like hydrocolloid, elastomers, zinc oxide regional, impression compounds. So all these materials are selected according to the requirement or the amount of deformation that can be permitted. So from this, it is understood that hydrocolloids like agar or alginate have more deformation than elastomers when removed from the undercuts of the mouth. What is strength? So strength is the maximum stress which is required to fracture a structure. So again, like with your stress or strain, it is of three types. So there is tensile strength, there is compressive strength, and then there is shear strength. What is tensile strength? So it is the maximum stress it can withstand before rupture. So it's the same thing here. It is either elongation or it is compression that is going to happen. Now, how can this be measured? So it can be measured by subjecting the specimen to a unilateral tension test. So it is the test done is called as a diametrical compression test or a Brazilian test. So it is an indirect test for assessing the brittleness of that material. So from this, you can measure the tensile strength as force or load divided by the diameter and thickness of the so-called material. Now, this again further goes as 2P divided by the P into D into T. Now again, what is compressive strength? So it is also called as crushing strength. So it determines the amount of deformation like or fracture or the energy required to fracture it when it is subjected to a compressive load. So a subject is experienced to or it is subjected to a compressive load. This results in the formation of complex stress, and because of the complex stress, there is failure resulting in the fracture of the said material. Next is shear strength. So again, this is the amount of stress a material can withstand before there is failure in the shear mode of loading. So this can be measured by either a punch method or a push out method. Again, shear strength can be calculated as force divided by pi into the punch diameter into the thickness. So now, what is the significance of this? So it will help us in studying the interface between two materials. This comes of significance in case of the metal fused to porcelain, in case of your metal ceramic FPDs. What is transverse or flexural strength? So it is also called as modulus of rupture, bend strength, fracture strength, or 3-point bending test. So what happens is when a load is applied on the middle of a beam which is appointed on the both ends, like a 3-point bending test. Okay, so it can develop the shear stress, it will develop your tension strength, as well as the compressive stress. So the complex stress is going to result in the development of a deformation to this particular material. That is the transverse or flexural strength. So what is fatigue? So fatigue, when a structure is subjected to repeated or cyclic stresses below its proportional limit, it can produce an abrupt failure of the structure. This is called as fatigue. So how can you determine fatigue? So fatigue can actually be determined when a subject is put forward multiple cycles of stress which is of a known value, and then you have to determine the number of cycles which is required to produce that particular failure. Now this is how the fatigue test is done. Now the stresses used in fatigue tests are usually very low, and on repeated application there is going to be failure or fracture of that particular subject. Now what is important? So a restoration in the mouth is constantly subjected to masticatory forces. This should withstand the fatigue or the restoration will fracture. So what is static fatigue actually? So it is exhibited some ceramic material. So it is actually what happens here is that when a material is stored in a wet environment, this will result in certain water effect. It is producing high stress on the surface. So this is result in the failure of the structure here. This is what is called as a static fatigue. So it is most commonly seen in ceramic materials where there is a high static load which is to be supported for a longer period. So this will result in abrupt failure of the structure. Now toughness is the energy that is required to fracture a material. Same as strength or everything, it just depends upon the context. So this will tell us how difficult it is for the materials. Toughness is, that is, the material has that much of resistance to breaking. So if you try to measure it in case of the stress strain graph, it is measured as the total area of that particular stress strain graph till the point of failure of that substance. Now brittleness again is opposite to that of toughness. So brittle material will fracture at or near its proportional limit. That is, it tends to fracture at a point before the stress and strain are going to be not proportional. Again, though these materials have strength, they may fracture easily. Now what is the significance is that the ceramic, porcelain, cement or dental stones, these materials may have toughness or may be strong but are brittle in nature. So we should know the point at which they fracture so that we can easily manipulate it. Next is ductility. So it is, in simple term, it is the ability of a material to be thrown or a metal to be thrown into wire. That is, it should withstand permanent deformation without undergoing rupture. So this is dependent on the tensile strength. Now a metal is ductile. So the ability of a material to be ductile will increase as the temperature is increased. So there are three methods. So it can be measured by elongation, like percentage elongated following fracture, based on reduction in area method. That is, we can measure the reduction in the cross-sectional area of the fractured ends and then compare it with the original area of the wire or the rod. Next is the cold bend test. So here you will count the number of time a wire can be bent to a right angle, and that is how many times that one particular wire can be bent at that particular side without it breaks. So it has significance in orthodontic wires. So malleability, again, it is the ability of a metal to be thrown into sheet. So if it's wire, it is ductility. If it's sheet, it is malleability. So this can be done by hammering or rolling that metal into strips. Now it is not dependent upon the strength or ductility, but again it is dependent upon the temperature. Now hardness, again, it is the ability of a material to resist scratching or indentation. Now the factors that are going to regulate this is the strength, proportional limit, the ductility, and finally the malleability. Now, the surface hardness test are either macro hardness test or micro hardness test. Now, macro hardness test is the Brinel hardness test or the Rockwell hardness test, whereas the micro hardness test is going to be the Knoop hardness test or the Vickers hardness test. So now, these surface hardness tests have a significance in the determination of which material is used in a particular condition. For example, whether a dental stone or a die stone is going to be used for an FPD cast, whether a metal ceramic or a all ceramic is going to be used in a posterior teeth. So all these things actually regulate most of the dental materials and their indications. So the first test is going to be Brinel hardness scale. So it is first described by John August Brinel in the year 1900. So here it characterizes the indentation hardness of the material through the scale of penetration, that is in that particular apparatus an indenter is going to produce an indentation on the material, and the depth of this indentation is going to determine the hardness of that material. So now here you can see it is going to be a round indenter, and the width of the indenter is going to help us in determining the Brinel hardness. So the load is going to be divided by the area of the indentation produced. This is going to give the Brinel hardness number. The unit is going to be HBC here. Now what is the advantage of this test? So the advantage of test is that it is a non-homogeneous, you can use it to measure non-homogeneous, non-destructive materials. Again, you can do it using different force and different indenters. Now, the drawbacks are that brittle and plastic materials cannot be measured using this method. So, the indication is mainly for metal and metallic materials. So, only hard materials can be measured by this particular method. Now, Rockwell hardness somewhat overcame these options and were applied on a broader terminology. Now, this will measure the depth of penetration under a major load or a large load and then compare it with the penetration made by a minor or a lesser load. Now, this indentation is then correlated with the tensile strength. Now it is a 4 types, so there is going to be a Rockwell hardness tester, superficial Rockwell hardness tester, a twin Rockwell hardness tester, and a plastic Rockwell hardness tester. So the application is more wider over here, so it is going to be applied for hard, brittle and plastic metal. Again, the indenter used here can be a ball, conical or a diamond pointer. Vickers hardness test observes the material's ability to resist plastic deformation, like how much deformation, like how much strength is required to form that deformation. So this was described by Robert L. Smith and George E. Sandland in the year 1921. So now it can be used on all metals and is a widely used hardness test. It was easy to use as the calculation was independent of the size of the indenter, because in all the previous tests the size of the indenter was very important. Here the size of indenter is not required for measurement of this particular value. Now this indenter can be used for any material, like same indenter can be used for any material irrespective of the hardness. And the shape of the indenter is like a diamond indenter of either a square or a pyramid shape. Now here you can see there is a diamond indenter which has a particular width and a particular angulation. Now again the calculation is going to be load by area of indentation. So now the application is used by ADA for dental casting goal. Then it is used for measuring the hardness of brittle materials, and again this is the particular test that is used to assess the hardness of the tooth. So next is Knoop's hardness test. So this is used to measure the mechanical hardness used particularly for very brittle or thin sheet material. So here only a small indentation is made because the material that is used is very brittle. So this is independent of the ductility of the material, and you can assess values of both exceedingly hard or exceedingly soft materials using this. So here this is going to be the shape of the diamond indenter that is used. So based on this, a small indentation is made and the area of the indentation will help us in determining the hardness. So there are less sophisticated tests that are also used, which is the Shore and the Barkol test. So these are going to be compact portable units. So here a spring-loaded metal intender is going to be used. The hardness number will depend upon the depth of penetration and can be directly read on the gauge. So the application is mainly in measuring the hardness of rubber and plastic materials used in dentistry. So this is where the hardness test is going to end. So why do you want to learn about the hardness? So this will give us a clue about the abrasion resistance. So it is the ability of a material to resist abrasion. That is when two surfaces keep in contact. This will result in the mechanical wearing of both the subjects or either one of the subject. This is what is called as abrasion. So a dental material, when you are putting a dental material in the mouth, it should not cause abrasion of the tooth as well as does not abrade itself. So this is very important property required by a dental material. So what is the reliable test that can be done for abrasion? So we should subject that particular material to conditions similar. That is, if a restorative material is to be kept, we should make it exposed to the conditions of the mouth, like constant friction while chewing, all those things. Most common example is going to the tooth brushing abrasion test. So like if you feel like that the particular patient's brushing habit is going to cause abrasion to the tooth, you should conduct a tooth brushing abrasion test to see if it's like a normal or it is abnormal. Now the application is comparing materials of same class. That is, if you want to buy a glass ionomer cement and you want to know if the group A or group B is good, you have to compare between these two materials to look for the abrasion resistance to determine which one is better. But again, the defect is that you cannot compare materials from two different groups. That is, I cannot compare GIC with amalgam. I have to compare GIC with another group of GIC only. Now, when a subject is exposed to some kind of load, it is going to undergo permanent deformation when it's beyond its proportional limit. So now, when this deformation is happening, there is build-up of internal stress. Now, this internal stress will result in formation of an unstable object wherein all the atoms are in a frenzy to try to come back to their normal position because they do not like the change. After a while, they will release all these internal pressure, force or pressure or stress, whatever it is, and finally rearrange themselves to the new change. Now, the release of these internal stress will result in the change in the shape or contour. This is what is going to call as a relaxation. This will result in either warp or distortion. Now, the application mainly comes in case of wax and thermoplastic materials like impression compound, which will be manipulated, and as a result of the manipulation, they will become either distorted or what? They are changed. The shape is changed to suit our requirement. So, rheology is the study of flow of matter. That is, to flow, the matter should change from either a gaseous or a solid form to a liquid form. Now, this helps us in dentistry to allow us to know more about the change state from one form to another. That is a molten alloy or an impression compound or cement, etc. Now, let's talk about viscosity. So, viscosity, as we know, it is the resistance to flow by a liquid. So, when I am pouring a liquid on the floor, if it flows very nicely, it is less viscous. But if I am pouring it on the floor, it is just staying there, staring at everything, it is less viscous. The unit is a poise or centipoise. So, water is less viscous than a honey. Now, it can be measured by means of viscometer or a rheometer. Now, creep is the time-dependent plastic deformation or change in shape when an object is subjected to constant load close to its melting point. So, it can be of two types. So, it can be static creep or dynamic creep. So, static creep is a time-dependent deformation in a completely set solid which is exposed to a constant stress. Whereas dynamic creep is produced when the load or temperature or stress that is applied is fluctuating. So again, it is measured by a fatigue test. So you apply a fatigue test to determine the creep that is produced by a particular material. So if you are taking a restorative material, and it will have some components which have melting point above the room temperature. Now, if such a thing is there, if most of the materials or the components of that material has a melting point more than room temperature, this will result in a destructive property of that material. That is, a material will not be that compatible. This is the case with amalgam. So, what is the flow? So, flow is like a rheology of amorphous material like wax. So, based on this rheology, there are different types of fluids. So, there is a Newtonian fluid or a non-Newtonian fluid. These non-Newtonian fluids are further divided into pseudoplastic, dilatant and thixotropic. So, now what are all these fancy words? So, Newtonian fluid means it is an ideal fluid. So, if you are taking shear stress and shear strain, that is when a liquid is placed between two plates and you try to move both these plates, then a stress is required to move the plate. That is called as shear stress, and the strain so produced is going to be the shear strain. So, if like with the proportional limit, if these shear stress and strain are proportional to each other, for that particular fluid, it is an ideal fluid or a Newtonian fluid. Most common example is going to be the water or honey. If the stress and strain is not proportional to each other, it is non-Newtonian fluid. So here, three scenarios are going to arise. So first is a condition where the viscosity is going to decrease when the shear rate is going to increase. This is a pseudoplastic material. Most common example is the elastomeric material. Next is the dilatant, where viscosity and the shear rate are proportional to each other, as with your denture-based resin. Last one is a thixotropic material, where the viscosity will be 1 before deformation, and again after deformation the viscosity is going to change. Most common example is the zinc oxide eugenol material. So now the last aspect is going to be the aesthetic. So before that, look at this graph where you're going to see that the various aspects of the shear stress strain. So in Newtonian, the shear stress to strain is going to be proportional and has a straight line. Whereas in pseudoplastic and dilatant, it is not proportional to each other, thereby showing variations. So coming to the last aspect, that is the aesthetic component. So color is produced when an object is going to either emit or transmit light. That is, it will absorb particular light and it will reflect particular light. A human eye can see light from the violet to the infrared area, that is from 400 nanometers to 700 nanometer. Now color has three dimensions. So it has a hue, a value and chroma. So hue is the basic color of an object. That is the color that you're going to see. Is it red? Is it blue? Is it green? Is it yellow? So there are certain colors which combine. That is, we know that yellow and blue is going to combine and going to give you green color. Like that. And now value is going to be the amount of lightness or darkness. Is it white? Is it grey? Is it black? So the amount of whether it is light or dark is measured by value. Now chroma is the degree of saturation, that is the amount of color that is present. It is determined by chroma. So now when chroma is going to increase, the intensity of the color is going to increase. Now how do you measure this color? So I am telling you, it is a degree of perception of particular light wavelength. So how do you measure this quantitatively? So it is measured by something called as the Munsell system. So it specifies a color based on its hue, that is the color, its chroma, that is the lightness or the darkness, and by value, that is the intensity or saturation of the color. Now this is a uniform and independent dimension. It's a three-dimensional picture which is going to help us in independently measure all these values. So here, a subject's visual response to color can be determined by this. So this is used for identifying night blindness, and again the degree of all these components should be met accurately for the tooth to look as natural as possible when a replacement is done. Now metamerism is a phenomenon when the object is going to appear of one color in a particular light source and another color. So here, when a white light is given, these two balls have same color. But when a yellow color is given, you can see that the first ball is more darker than the second ball. This is what you call as metamerism. Now, based on the amount of light passing through it, objects can be of three types. So first one is transparent, where all the lights are passed through that particular material, like a plain glass. And then there is translucent material, which will allow only partial light to pass through it partially, like the tinted glass. Then there is opaque materials which will not allow any light to pass, like a book or a wood or something like that. Now, what is the significance of understanding these things? That is, when a restoration or a fixed process is done, it should mimic the translucency of the natural tooth. That is, especially the incisal edge of your tooth. If you see, they are more translucent than the middle third or the cervical third of the tooth. See, here in this first picture, it perfectly mimics your normal tooth. When it is kept inside the mouth, it should mimic the surrounding tooth. But here, if you see in the lower tooth, you can clearly visualize that these are processes and not the tooth, because the color is not matched to that of the surrounding tooth and there is no translucency there. See, here the incisal edges are literally translucent. Here it still appears opaque. Now fluorescence, this is the last portion. So fluorescence is a material has a tendency to absorb light of one wavelength, and that is it will absorb a light of lower wavelength, higher energy, and then it will absorb some of the energy and then emit a light of higher wavelength but smaller energy. Now, the importance comes in the fact that teeth have a natural translucency, that is, they have a blue color fluorescence. So, if this thing is mimicked by the prosthesis, it is gonna give better aesthetics. Hey guys, if you have any doubts pertaining to this particular topic discussed today, please do leave us a comment or you can DM us in our Instagram page.